I'm going to use this example to illustrate the definition for degrees of freedom and why it is equal to n minus 1, or 1 less than the sample size. And so we're told that a student needs an average of 70 to pass a class. And so we know that x bar needs to equal 70. He's already taken 2 of the exams, and so we know that his first exam score, which we'll refer to as x1, is equal to 71, and his second exam score is equal to 64. And so based on those 2 exam scores, we're going to figure out what he needs on the third exam in order to pass this class. And so we need to find x3 so that x bar is equal to 70. And so we're going to use the formula for x bar. And so we know that whenever we find the mean, we add up our data values and divide by the total number of data values. Here, when you do this, you'll get 71 plus 64, which is 135 plus x3 over 3. And so technically we should also plug in x bar, which is going to be 70. And so we want to find x3 such that this equation is true. And so keep in mind, if I wanted to know what he needed to get an 80 average, I could just set this equation equal to 80 instead. But I want to know about a 70 average, and so here, when we find this, you'll get 70 times 3 minus 135, which will be 210 minus 135, which gives you a score of 75. And so we now know that he needs to get a 75 on the third exam in order to get a 70 average on all 3 exams. And so now I can illustrate why the degrees of freedom is equal to n minus 1. These first 2 exam scores over here, x1 and x2, they can be anything they want, right? And so if he had gotten an 80% and a 70% on the first 2 exams, I would still need to go through and use this formula, and that would still mean that x3 is fixed, right? And so it'll be a different value, but it'll still be stuck at whatever value we find. And so that's true for everything, right? The first n minus 1 values are free to change, while the last value is always stuck. It's not allowed to change. And so that's why the degrees of freedom is 1 less than the sample size.